That voice you just heard?
I am Morgan Cable, NASA scientist.
I love it.
That's Morgan. She's probably one of NASA's best spokespeople for exploring our solar system's icy moons.
Europa is a fascinating place. It has this liquid water ocean that's about 3 times the volume of all of Earth's oceans combined. That's a lot of water.
To understand what makes Earth so special, sometimes you need to back up and take in the big picture. Remember, the cryosphere is every place on Earth with frozen water. And water is one of the biggest indicators for life.
Every place, at least so far, that we have found life, we found water along with it.
And so far, Earth is the only planet we know of with life. Although Europa isn't the only icy moon in our solar system, NASA has identified it as one of those places with key astrobiological potential. Morgan is a collaborator on the Mapping Imaging Spectrometer for Europa, an instrument selected for NASA's next mission to Jupiter's icy moon Europa. But she's also more than just a scientist working in a laboratory. She's preparing future NASA missions for success on the surface of alien worlds. This year, Morgan and her colleagues were in the field studying how life colonizes in fresh lava.
Earth, it turns out, has a lot of excellent, what we call analog environments, places that are similar enough to some of these other worlds that we can conduct some tests and we can do some analyses here. Now, they're not perfect, of course. They're not going to be exactly like Europa, but we can still learn a lot by testing in these environments. Some of these places include Antarctica and the Arctic Circle, but there are other places too, Alaska, Greenland, even Iceland. Any place where you have a lot of ice, because guess what the surface of Europa is made of? A lot of ice.
Studying the cryosphere doesn't just have big implications for Earth. It also matters for the frozen worlds in our own cosmic backyard.
If we're able to find life or evidence of past life on a place like Europa, that tells us that not only can life happen in other places, but it's common enough that it happened at least twice in the same tiny solar system. That means that the universe is wide open in terms of how much life we might find, the types of life we might find. It would revolutionize how we see ourselves and the possibilities for contact in the universe. It would be amazing. Oh, it's so exciting.
My interest in glaciers comes from the sheer size of these things and how much they're able to change on human timescales. And so the amount of mass and energy being transferred by glaciers around the globe is tremendous. It's been absolutely fascinating to study from space.
Mountain glaciers are some of the most charismatic parts of the cryosphere. Some might cling to the edges of cliffs at higher elevations, then lay bare and flat in a broad plain, looking cracked and weathered like elephant skin, before tumbling thousands of feet toward the sea and terminating in a dramatic calving front. They're like motion frozen in time, until they aren't. They tell a story about the distant past and yet are incredibly responsive to the present. You can understand why they'd be captivating to all of us, and especially cryospheric scientists. Meet Alex Gardner, a cryospheric scientist at NASA's Jet Propulsion Laboratory, who is going to help break down what a classic West Coast North American glacier might look like, where high amounts of snow dump onto the mountains.
And at higher elevations, there's melt in summer, but not enough melt to get rid of all of that snow. And so that snow accumulates, it compacts, it turns into ice, and it starts to flow under its own weight, and it flows down the valleys. And as it flows down the valleys, it actually carves those valleys out, and it makes them deeper. And so it creates these beautiful fjords where the ice flows down, snakes out down to the ocean or to the lakes or further inland. And so that ice is flowing, it's moving.
Alex uses satellite data to study large-scale changes in glacial ice. But 2,000 miles to the north, Chris Larson from the University of Alaska Fairbanks spends a lot of time studying glaciers from the air. He's been flying over Alaskan mountain glaciers for many years, most recently on a NASA-funded mission called Operation Icebridge Alaska. He's absolutely enamored with his local rivers of ice.
And what do you love about mountain glaciers?
Well, they're in mountains, so they're really pretty.
You couldn't ask for a better way to experience Alaska on a large scale than to go flying around for campaign after campaign and look at all of the mountains in Alaska. Truly infinite. You just feel like you'll never see the end of them, and don't want to either.
But Chris doesn't spend weeks away from home and family for the views. Chris and his colleagues at NASA want to answer some pretty big questions by learning more about Alaskan glaciers and how they tick.
You know, why does NASA care about these? Well, they actually disproportionately contribute a large amount to sea level rise.
In the long run, as the Earth warms due to climate change, the big ice sheets and mighty outlet glaciers of Greenland and Antarctica stand to contribute the most to sea level rise, simply because the vast majority of the planet's ice is stored there. But currently, it's the world's smaller mountain glaciers in comparatively warmer places, like Alaska and Patagonia, that are contributing about a third of all inputs to sea level rise, even though they account for only 1% of the world's ice.
Mostly due to them being dynamic. They have water at the bed, which allows them to slide fast, and they react quickly to climate change and have higher velocities than their polar counterparts.
Back at JPL, Alex uses satellite measurements of global ice and computer models to predict ultimately how much sea level rise we might see due to climate change. But in the case of mountain glaciers, we also care about the local impacts of disappearing ice.
When we think of changes in ice sheets, we typically think of just what is the consequence for sea level rise and the future evolution of the ice sheets. But glaciers in other regions, like high mountain Asia, Alaska, the European Alps, these are places where changes in runoff matters to stream flows. In places like high mountain Asia, you have a lot of glaciers that feed the streams that flow down to populated regions. And that runoff becomes significant for water resources, irrigation, and agriculture.
Both Alex and Chris are passionate about understanding how glaciers are changing and what it means for our planet's future. They'll continue to use tools like elevation maps from the ICESat-2 satellite and detailed airborne measurements to monitor changing ice.
What we're looking at is a legacy of the Ice Age. Permafrost and methane is a time machine. So what we're going to do is walk back in time. We're going to see old carbon, old bones, old environments, and none of those are in equilibrium with today's climate, so that's the problem. That world doesn't exist anymore, and it hasn't for 10,000 years. It was nicely and very delicately separated from this modern warmer climate by about this much moss. And when that moss goes away, whether for fire or for human disturbance or for warming, then all hell breaks loose.
Permafrost. It's maybe the part of the cryosphere that's most out of sight and mind. It's fascinating how it formed in the first place and how it got loaded with so much carbon. In a minute, we'll go back underground with Matthew Sturm from the University of Alaska Fairbanks. But first, let's meet Peter Griffith, NASA's project manager for the Above campaign, which supports more than 70 science projects studying forest and tundra vegetation, wildfires, animals like birds, caribou, and Dall sheep, methane emissions from expanding northern lakes, and the impacts of climate change on people in Alaska, Canada, and around the world. Many of those projects have some direct connection to permafrost.
Permafrost is the hidden cryosphere. It's the permanently frozen soil that surrounds the Arctic, all across Alaska, northern Canada, and then across Eurasia. The ground has been frozen during the ice ages.
During the ice ages, there was not enough snowfall in the drier regions of Alaska and Canada to form glaciers there, so the land was suitable for vegetation.
What happened is that over thousands and thousands of years, all of that plant material got compacted and frozen every winter and buried and pushed down, so that today there's 300 feet deep of frozen water and dead plants and some pieces of dead animals too. Sometimes you find woolly mammoths in the permafrost, as we call it. In the permafrost is frozen plant material.
Some of that plant material is now thawing and decaying into the atmosphere, sometimes in the form of methane gas bubbling out of expanding northern lakes.
We started this field campaign because the Arctic is the part of the planet that is warming first and fastest. And there are consequences to this for permafrost. So during the Arctic Boreal Vulnerability Experiment, we're studying permafrost with people on the ground, from aircraft flying over the region, and also from satellites in space.
Another way to understand the permafrost is to take a walk below ground with Matthew Sturm and into the U.S. Army Corps of Engineers permafrost tunnel.
And they've dug this tunnel back into the side of a hill about 200 feet, and it goes into the tunnel. You're about 100 feet underground, and you're surrounded by bones sticking out of the wall from the steppe bison and mastodons that are frozen in it. There's sticks that are 40,000 years old, that you can touch with your hand. There's grass that's still green, that's tens of thousands of years old because it got frozen, right away, and it's never lost the green color.
But as fascinating as it is to see these relics of an ancient era, or to see a tree split in half by thawing soil, or relics of an ancient era thawing soil, or even to light a ball of methane on fire from under winter ice, at the end of the day, Peter and his colleagues want to know just how much organic matter is frozen in that permafrost, and how fast it might be released.
Currently, we think that there is something on the order of 2 to 3 times as much carbon locked up as frozen organic matter in permafrost as there is carbon dioxide in the atmosphere. So releasing all of that organic carbon from permafrost into the atmosphere would be a real game changer. That would be a tremendous transformation of the planet's atmosphere. Now, the good news is that it would take a very, very long time for that to happen. However, we are warming the planet at a rate now that calls into question how quickly is that changing and what the consequences in the near future and in the far future are going to be.
We're at Vandenberg Air Force Base. We're about 20 minutes before the launch of ICESat-2. You might see the white light off in the distance. That's the Delta II rocket.
It kind of feels like an idea that was always going to just stay an idea. But no, it's real. It's sitting on top of the rocket.
And for me, it's kind of surreal. Like you say, it's been 10 years, and it's hard to believe. It's like, we're really here? This is really about to happen? It's totally cool.
This is Dr. Tom Newman. Over the years, his work has taken him to some pretty remote areas to study changes in the ice regions of our planet. And his research, among many others, has defined the goals of the new NASA satellite, the Ice, Cloud, and Land Elevation Satellite 2, or ICESat-2.
And we have ignition and...
The story of ICESat-2 really begins with ICESat-1. ICESat told us all kinds of cool things about the ice sheet and about sea ice that we didn't really know to ask. That data allowed us to measure elevation change of ice sheets in a way that we hadn't been able to before, and showed that all the action on the ice sheets, the places that were really changing quickly, were around the edges. So when we were thinking about what could we do better next time, we knew that was one key component.
In addition to the edges of the ice sheets, ICESat-2 needed to measure a dimension of sea ice that remained elusive: its thickness. To figure out how thick sea ice is, you can measure the height of ice sticking out of the ocean, or freeboard, and compare it to the height of water between the sea ice flows, called leads.
The problem is, sea ice is really dynamic, and those cracks open and close various places in the ice pack throughout the day, throughout the year, and what we need to do is have measurements of the ocean whenever it's available, wherever it occurs in the sea ice pack.
To solve that problem, ICESat-2 was designed with a fast pulsing LASAR instrument to take precise, near-continuous measurements across its 3 pairs of beams. For 10 years, everything about the mission was designed to measure rapid changes in the most rapidly changing part of the cryosphere. But it has to get into space first.
But it's a huge transition going from the ground to in space. We've spent better part of 10 years, thousands of people have been involved, and actually seeing the rocket there on the pad with all of that work kind of all put together in one place, it's pretty amazing. And then getting up in the middle of the night to go watch the actual launch, it's sort of surreal in a way, because you've put so much time into it for so long, and actually seeing it over there is like, whoa, you know, it's a big deal.
4, 3, 2, 1, 0. That's off. That's 1.
Thanks, sweetie. That was awesome. Totally cool. There it went. That was Atlas. The last Delta II, heading on up. So Atlas has been turned on over the course of the first few weeks of the mission, really culminating for us with the laser. So this is our first look at sea ice data from ICESat-2, and it looks fantastic. The signal levels look great. We've got plenty of photons there. We're capturing ridges. We can clearly see the ocean. All sorts of cool stuff in there. And this is just our first data. It's only going to get better from here on out.
The data from ICESat-2 is well on its way into digging deeper into the unknown dimensions of sea ice, ice sheets, and glaciers. It will shed light on changes in sea level and global weather patterns, and once again find new things about ice we didn't know to ask.
So my heart is definitely racing. I don't know about anyone else's. This is the stuff nerds dream of.
10 seconds. 9, 8, 7, 6, it's gonna 5, 4, 3, 2.
That countdown you just heard? We'll get back to that in a minute. Last episode, we saw the epic launch of ICESat-2, NASA's newest state-of-the-art ice-observing satellite. But now that that's in orbit, the pressure to deliver results is on.
Between launch and, the first ground returns, took 17, 18 days or something like this. It's a time when you're quite nervous.
9 years ago, Dr. Torsten Marcus took over as the lead project scientist for ICESat-2 during a time when the mission needed a champion.
You start fighting for a mission over, for 9 years now.
So when ICESat-2 was turned on for the first time 18 days after it was launched, only then would the science team know if the whole thing had worked. And it did.
first of all, it's kind of emotional, right? Being here, ISAT 2 was development for 9-10 years, and it's a project scientist. You live in this, right?
If it sounds like there's a lot of noise in the background, that's because Torsten is being interviewed from a plane 1,500 feet in the air. IceBridge was tasked with the job of bridging the data between the end of ISAT's mission and the beginning of ISAT 2, about a 9-year difference.
The goal is that it would run until ISAT 2 launched and then would have overlap with ISAT 2 as well, so we can get a really long, well-calibrated time series from IceBridge.
As the deputy project scientist for Operation IceBridge, Brooke works closely with Torsten to make sure the two missions are syncing up.
The timing was everything during that mission, which was a real challenge because not only do we need to...
Basically what you need to take away is getting an airplane and a satellite in space to fly over the same flight path at the same time and collect matching data is really, really hard. IceBridge was tasked with two objectives: check the accuracy of ISAT 2's data over land ice and over sea ice. They were able to lock in the land ice data fairly quickly in the mission, but the sea ice data...
It was really tricky. We waited day after day. Do we fly the sea ice? It's still on our list.
7, 6, it's gonna 5, 4, 3, 2, 1. Mark on the overpass 0435, 350.
Here's what just happened. A plane 1,500 feet up and a satellite 308 miles up measured the same sea ice at the same time. This moment finally linked veteran mission Operation IceBridge's data to that of its new sister mission, ISAT 2. Two projects that, until now, were separate for nearly 10 years.
It's a very satisfying feeling because you do something that is meaningful and in the bigger picture. And yeah, it's very satisfying.
Our search for knowledge doesn't end here. Grace Follow-On and ISAT 2, the two satellite missions that launched this year, will continue to bring in incredible data for the foreseeable future. The steady drumbeat of campaigns in the field goes on, but most of all, the people who look for answers will never stop searching. And from our perspective, it's pretty clear why.
What is your favorite planet in the solar system?
My favorite planet is the planet Earth.
What? Earth? Really?
The Earth, obviously.
Favorite planet in the solar system? Earth, right? We live on it. It's a really important one.
Favorite planet is Earth.
Right.
Yeah. Yeah, so when you look out at the other planets, they're absolutely fascinating. They've got all sorts of interesting systems going on. They've got dust storms. But then when you're on another planet, looking back at Earth, I mean, it's just incredible.
Whenever you go in different places, it looks so different, so amazing. It's just, I love planet Earth. It's just a very special planet. This is our home.
We've seen things far beyond the solar system. But even with all that, even the amazing things we've seen, one of the most amazing is the Earth itself.
It's got to be Earth. It's got to be Earth.
It's got to be here. I like the polar regions up here, of Earth. Yeah, sorry. It's very boring.
Earth is good.
Earth is good.
We live here, it sustains our life.
I'm not going to turn my back on it.
It's got water, it's got ice, it's got vegetation. I mean, it's rich with life. And so studying Earth is a very, very rewarding career. And I think if we were on any other planet, we would be trying to get to Earth as quickly as we could.
"14 days, 2 piston bullies, 4 people. So yeah, 750 kilometers, door to door. Recently, we just got back from Antarctica, where we completed about a 2-week ground traverse near the South Pole. We're basically driving piston bullies, tracked vehicles similar to the ones that groom your ski areas. Behind those piston bullies were 60-foot long plastic sled trains, and ultimately those trains carried things like our sleeping tents, fully erected and left standing during the day when we were driving, kitchen tent, fuel, generators, all sorts of cargo.
But everything we needed for the trip.
And from a both science and survival standpoint. So this entire traverse was in support of ICET-2, which will launch later in the year.
ICET-2 is all about measuring elevation, and a natural question is, how do you know you're getting the right answer? This is how we will know. We'll go out and collect a reference data set. We'll be ready to compare and evaluate, see how we're doing.
319 is feeling kind of ready. How you guys doing over there?
So the big measurement we were making was to measure the elevation of the ice sheet surface around our traverse, and we had the 2 GPS running, one on each vehicle, measuring that elevation. One of the other experiments we were doing is leaving out what we call corner cube reflectors to get an assessment of the pointing of ICET-2. When we make an elevation measurement, how are we sure it's in the right place? So in this picture, you can see a bamboo pole with a little white cap on the end of it, and embedded in that cap, a little piece of glass about as big as your pinky nail, and calibrated to green laser light from the satellite. Bounces off of this thing and goes right back up to the satellite again, super reflective. So these things, as Kelly has demonstrated, show up in data with altimeters like ICET-2. When you first get to South Pole, and you're coming from McMurdo, which is a nice seaside town right at sea level, and South Pole is what, about 10,000 feet. And yeah, you notice it pretty quickly. The temperature is a lot colder than in McMurdo. It's probably 30 degrees, 40 degrees colder, and 10,000 feet higher. Walking from the camp to where we're putting in an array, for example, would be a 10-minute walk, maybe 5 minutes. A couple breaks on the way. You know, it's still pretty high.
The plan is to repeat this traverse for the next 3 years, so 4 years of data total. And that would last the mission lifetime, the mission requirement lifetime for ICET-2.
ICET-2 has 1,387 orbits, and so it's cruising around the world, and it's got these unique tracks that repeat every 91 days, and all of those tracks converge right here at 88 South. And so our route crossed, what, 20% of them? So we can calibrate data from 20% of our tracks with this stretch that we drove, and by repeating it every year about the same time of year, we'll have overlap at exactly the same time, but we'll also be able to figure out what's been going on in between, because we'll measure it in 2017 and then again in 2018, and you can see how it changes from year to year. So that'll be pretty cool too. It'll quickly become the best surveyed piece of either of the ice sheets.
This video is from the 16 October 2018 Northern Peninsula Ice Bridge mission. We're about 1/3 of the way into the flight right now in this video, and we have just finished our first transect across the Larsen C ice shelf from west to east. And we are making a right turn to get lined up for our second transect across the ice shelf. You can see here we're crossing some fairly large tabular icebergs. These are remnants of the breakup of the A68 iceberg off of the shelf last year. The big square-looking iceberg at left is the one that became somewhat famous in the media over the last few days. Now we're crossing some combination of open water and sea ice. This big, huge tabular berg ahead of us is the A68 iceberg. It's about 100 miles long, about 30 miles wide. And you can see the video here has been sped up by a factor of 20, and even at that, it still takes us quite a while to get across this thing. And you have to remember there as well that we were only crossing the northern corner of it, and even so, it took us a while. So now we're back off A68 iceberg, heading westbound. You can see the sun there. It's the afternoon, crossing a mixture of sea ice and icebergs, and this big white mass ahead of us is the Larsen C ice shelf, which we're just about to head back on.
There's enough ice here in Greenland to raise sea levels by 25 feet all the way around the world. It's an incredible amount of ice, and it's melting and adding to sea level rise. For oceans melting Greenland, what we really want to do is measure the oceans, measure the ice, and watch them change together year on year, and try and answer the question, how much are the oceans melting away the ice, as opposed to the air, which is what most people have studied so far. It's really a breathtaking landscape. These giant mountains and canyons are all along the coast. When you look out the window, you really get a sense of just how huge these glaciers are, these gigantic rivers of ice that are draining the ice out of Greenland into the ocean. And then they reach the ocean and it gets all broken and craggy and big chunks fall off. It's incredibly dramatic. Kulasuk is just a tiny little town in southeast Greenland, and we've been launching probes out of here for the past 4 or 5 days. It's already been a fantastic year for OMG measuring the oceans. We launch them right out of this tube right over here. Open up the tube, you can look right down it and see the water passing by, or sometimes the icebergs or clouds or whatever it is we're flying over. We slow down a little bit and we just push these big gray cylinders out of the bottom of the plane, and they fall to the ocean and measure the temperature and salinity when they get there and radio it back to the plane. We're really trying to look at the ice and ocean all the way around Greenland. So we're dropping 250 profilers. We're going to cover the coastline all the way around. And in the spring, we map out the glaciers with a radar, also all the way around. So we're really looking at mapping all of the ocean ice interactions in Greenland as best we can with one mission. What we care about with OMG really is the breaking off at the edges. As the water eats away at the ice, then it can actually speed up that breaking off part. And when you dump more ice in the oceans, then it causes sea level rise. So OMG is really here to try and figure out how much are the oceans doing, how much is this kind of breaking off of the ice, it's called calving. How important is that relative to the melting at the surface? And more importantly, is the ocean causing some of this speed up of the calving? We think it is, but how widespread is it and how big an impact? Even the smallest iceberg looks gigantic when you're right next to it. We saw an iceberg that was grounded in the bay. Remember, 90% of the iceberg is below sea level. So if there's about 10 meters or about 30 feet of ice above sea level, then 300 feet are below. It's a reminder that a lot of the stuff we're trying to measure is hidden below the surface of the ocean, hidden below the surface of the ice, and peering down into both of those is really at the core of what OMG is trying to do. Every time a ton of ice comes off of Greenland, sea level goes up a tiny little bit, and it's coming off Greenland at billions of tons per year. It's interesting to meet some of the Greenlandic folks who have been here their whole lives. They've all watched the glaciers literally vanish before their eyes. They didn't need satellites and airplanes and scientists to tell them that Greenland was melting. They look out and see the glacier used to be here and now it's way up there. Sea level rise is really a global problem. It's something we can't just ignore. 2/3 of the planet are covered by the oceans, and it's really the same ocean. I mean, if ice is lost here, sea level rises back home in Los Angeles, rises in Southeast Asia, in Australia, all across the planet. Being here and seeing the ice disappearing and literally watching it fall into the ocean is really profound, and I think it's something that I hope that we help people understand with OMG, that we all live on the same planet and it's changing and we need to know how.
The Cold Atom Laboratory is in many ways the coolest thing and the coldest thing we've ever done on the International Space Station. It is allowing us to investigate cold quantum gases and make breakthroughs in areas of physics that up until now have been unavailable to us.
NASA built the International Space Station to do the Cold Atom Lab. This is the first time we're able to study this fifth state of matter in space.
Bose-Einstein condensation is an amazing feat of engineering in itself, but this type of physics is difficult to do in ground-based experiments. And so doing this in microgravity is going to allow us to really see what's going on. So you have something cool, how do you make it cooler? You put it in space.
Our ability to study cold atoms is really going to advance our knowledge in areas that will help us in quantum computing, quantum communications, and learn even more about gravity and how it interacts in our universe.
Welcome to NASA Edge.
An inside and outside look
at all things NASA.
On today's show, we're going to be talking about nanotechnology,
which is technology that's really small, or as I like to say, coho-sized technology.
Well, I think it's a little bit smaller than coho, maybe like the G.I. Joe with the Kung Fu grip, or maybe Ant-Man size small.
All right, Ant-Man I'll buy, but it's probably even smaller than that, probably deeply embedded in wearables for Ant-Man.
Well, you know, in today's show, we're going to be looking at nanosensors, nanowires, nanotubes, and composite overwrap pressure vessels.
Or COPVs.
Yeah, which is really what's interesting to me about the technology. It's not a single technology with a single use. It's a technology that's being applied all across industry in a lot of different areas, and even across NASA.
And speaking of COPVs, we're going to have Mia Siochio on the show today, and she's going to talk to us about how NASA is using nanotechnology in some upcoming tests.
But first up, I had a chance to talk with Steve Gaddis, who's going to give us a broad picture of nanotechnology. We're here with Steve Gaddis, the manager for the Game Changing Development Program Office. Steve, how you doing?
Doing good.
So Steve, we have this whole technology campaign where the theme is technology drives exploration.
Absolutely, and I believe it.
What's that mean, technology drives exploration?
It means if you want to do these cool things that we haven't done before, we have to develop the technologies to go do them. We can't simply just keep doing what we've already done in the past, right? We've done some cool things, but we want new missions. We want to go farther than we've been. We want to drill down. We want to bring things back. So we need these new technologies.
Now, with Game Changing, you're sort of a subset of the Space Technology Mission Directorate at NASA headquarters. And so what's the focus on Game Changing as opposed to the other technology subprograms?
We're the disruptive program. We're the DARPA-like program out of the 9. However, all the programs, they're looking for revolutionary and incremental developments in technology. But our associate administrator really wants us to take some risk. He expects a certain amount of failure in the activities that we're pursuing, the high payoff, high risk type activities. And so he'd like to see the risk take place with us instead of maybe in some of our sister programs where we're demonstrating on orbit, or we're demonstrating on the International Space Station, or we're demonstrating on a ride with another government agency or the commercial crew type folks.
So when you talk about specific technologies in your program, are you taking programs from scratch, or are you getting programs from another group that have already been through a certain, mature process?
So it's a mixed bag. Some things we generate from scratch. However, what we like to see them get to a TRL, technology readiness level, of around 2 or 3 before we pick them up. And in many cases, someone's done the basic research, whether it's industry or whether it's a university or whether it's some of our research centers. They've proved the concept. Getting from 3 to a TRL 6 or 7 is really where the challenge is, and that's where GCD fits, that mid-TRL range.
Now, when we talk about TRL, we're looking at a scale from 1 to 9.
1 to 9. 9 meaning it's flown in space multiple times, heritage. 6 or 7 means it's going to be demonstrated, or it was demonstrated, in a relevant environment such as space.
And in your TRL range, it won't fly in space, but it will be tested here on Earth.
It depends, but that's primarily the focus. We do TRL 3 to 5 and 6, and 5 is a near relevant environment, could be a suborbital environment, but several things that we do also go on to station, right? So that's obviously in orbit, it's in space as well. So a small part of our portfolio does make it to space.
Now, what are some technologies in your portfolio?
Man, there's some really cool things. Some of which are far out, some are a little closer home. We're looking at wearable technologies, and that would be like in the old Star Trek days, you know, when someone's got the comm on their shirt and they hit the comm and they can communicate. Others, it's relaying information back and forth. The astronauts need things like that. And we've been working on something called an exoskeleton. And essentially what this began to do was just provide exercise for the astronauts, right? And you know, they got to take all that equipment up there. It takes space, volume, power, et cetera. But if we can take this one it compacts, it stores very nicely, and it can give them that resistance exercise. But then the reverse of that is if they had to be in a situation where they needed a little extra horsepower, it could give them that as well. That's been a spin-off to the Veterans Administration, helping wounded warriors get back into action. We're developing new robots, humanoid robots. Then, in a particular area that's of interest to me is nanotechnology, which is just a blossoming field. They're making almost daily discoveries with nanotechnology. They'll take these carbon nanotubes, they'll mix them with a fluid, and then this fluid will end up with a new characteristic that they can apply to something. So we're looking at making materials out of these nanomaterials. We call them nanocomposites. And if we think composites themselves reduce mass and cost, this takes it another order of magnitude. So we're very interested in it. We're looking at nanosensors, very small sensors that you can put on something that can track your blood chemistry and report that out. Also, sensors that can be weaved into something that you can't even tell it's in the material because it's a nano-type sensor. We're looking at a COPV, which is a carbon overwrap pressure vessel, right? So it's a tank, and we'll take this nanomaterial and we'll wrap it over this aluminum inner structure.
To strengthen it? Or?
Yeah, to strengthen it. And it also reduces the weight because it doesn't all have to be aluminum. We've got one of those that's going to be flown on the sounding rocket next year. We're very excited about it. We're also looking at nanowires. We just set a world record with a nanowire with the most electrical conductivity ever demonstrated to date.
That's amazing.
I mean, it is amazing. It's groundbreaking.
It's game-changing.
It's game-changing.
That's right.
It really is. So we're looking at the nanowires. We're looking at the nanosensors. We're pursuing the nanocomposites. Really cutting-edge, cool technology. Lots of things like that.
You know, Steve, he's a real game changer. He did a great job giving us technology.
You know, one day I'd like to see how nanosensors will work in things like watches and phones.
Well, you've come to the right place because we had a chance to sit down with two important people who are using the cell phone and nanosensors.
Yeah, we had a chance to talk with Maya and Jessica about how NASA is incorporating this technology into cell phones and using them in different ways. But what I'm really curious is, can we really understand just how small this technology is to do just that? May I understand nano is small. So with nanosensors, I'm assuming you're dealing with really small sensors. But what exactly are nanosensors doing?
Yeah, nanosensors are a product of nanoscience and nanotechnology. When materials go to that small scale, their properties are fundamentally different from bulk materials. So scientists all around the world, have been working very hard trying to take advantage of this difference in properties between the bulk scale and the nanoscale and trying to make useful things, which are devices, systems and architectures, materials for a wide variety of applications, touching upon every economic sector, which is electronics, computing, materials, manufacturing, health, medicine, national security, transportation, energy storage. And I don't want to leave out space exploration.
I was going to say, that's a lot of stuff anyway.
Yeah.
You mentioned space exploration, so I'm wondering, how are nanosensors being used by NASA?
The nanosensors are being developed to replace bulky instruments NASA has been using no matter what you want to measure, whether you want to measure a composition of a gas or a vapor, or you want to measure radiation, historically we have always taken bulky instruments. And remember, every pound of anything that we lift to near Earth orbit, it costs us about $10,000 a pound. The same 1 pound of anything would cost roughly about $100,000 a pound, for Mars and other missions. Okay, so we have an incentive actually to miniaturize the size of the payload. So that's why we want to move from bulky instruments to sensors. That's one reason. The second reason is no matter where we go, okay, we don't have utility companies sitting there waiting for us. Okay, we have to generate our own power, and we have to be very wise how we use that power. So the sensors, not only they're small in size, but they also consume very low power. So that's why over the last decade or so, we've been working on developing nano-based chemical sensors, biosensors, and radiation sensors.
Now, when you're looking at these biosensors, and we're looking primarily for crew health, crew safety, what would they be used for?
What are the applications? Yeah, we've developed them for crew health and diagnostic purposes. That's our most recent project that we worked with the Game Changing Technology Office on. And so for that project, we developed this sensor to look at a variety of different protein biomarkers for cardiac health. And so when you're in microgravity, there's a lot of strain that's placed on the heart. So to monitor the health of the heart for our astronaut crew is critical. So that is the most recent technology that we developed for them. We've also worked on this sensor looking at microbial contaminants in the water supply. So this is an environmental kind of application for NASA to make sure that the water that the astronauts are drinking is actually safe to drink.
Now, when you're looking at the astronaut's heart, is it a sensor that you place on their body, or is it something they ingest, or how's it?
This is an external sensor that will take 1 drop of blood and be able to screen for a number of different proteins. And depending on the levels of proteins and which proteins are present, we can make an informed diagnosis of the health of the crew member's heart.
Do these sensors have a long shelf life, or is it something that lasts for a short period of time because of the complexity of the sensor?
It depends a little bit on how we fabricate them and how we package them. The sensor itself, without any kind of surface modifications done to it, has a very long shelf life. I have sensors in my lab that are probably 10 years old that I can still pick up and use today. What limits the shelf life of these types of sensors is we often introduce some sort of biological probe molecule on that surface. So depending on what that probe is, that's going to dictate the storage needs as well as the shelf life of the device. We've been placing a lot of emphasis on making probes that are very robust so that we can increase that shelf life for our missions, so that we're not looking to replace these sensors every 6 months, that we can actually keep them for years at a time and continually reuse them.
And one of the coolest things that you were showing us this past week was the fact that you have a cell phone technology adapted to these nanosensors. So you have an application that you developed on the phone that can actually be used in concert with the nanosensor.
So this was designed actually for the chemical sensor project. And this phone has a plug-in port on one side that contains the sensor chip, has a fan that will direct airflow from the environment over the sensor surface. And then just using the electronics that are part of the phone, we have a nice little instrument that will actually read what kind of chemical environment the sensor is exposed to.
Now, would you have multiple nanosensors within that adapter for the phone, or is it just one nanosensor?
So we have one chip, but these chips can be made with a number of different sensors. They can have hundreds of sensors. They could even have thousands of sensors on one chip, all working together to tell the user of the phone what the environment is.
Guys, that was some great information on nanosensors. I can definitely see how that is a game changer, because once it's commercially available, it will definitely change our lives.
I tell you what, we could have spent a whole show on nanosensors. That's how cool the technology is.
That's right, Chris, but we're only scratching the surface at looking at this technology. I had a chance to sit down with Jim Geyer, and he explained how NASA is using nanotechnology to develop better, stronger wires. Let's check it out. Jim, I understand that you're working with carbon nanotubes as a potential replacement for conventional wiring, but I didn't know wiring needed an upgrade. What exactly are you doing to improve wires?
Well, I don't think a lot of people understand that wiring really is a
takes up a large amount of the mass in current spacecraft and aircraft. Like a 747 has nearly 2 tons of wiring in it, and a space shuttle had over almost 300 miles of wire. This is a lot of weight, and so conventional wiring with copper, it turns out, is very heavy. Copper is dense, and it's also not very strong. And so we're looking for a way to have a better mechanical properties, actually, than conventional wires have.
So these carbon nanotubes, when you make a wire out of them, how do they perform in terms of strength?
They're much stronger, they're more thermally conductive, so you don't get hot spots and so on. They're very flexible. They're actually much more flexible than copper, and they don't fatigue. Fatigue is when you get a breakage from moving back and forth.
That's how I break wire intentionally sometimes.
Exactly. And in fact, they ran tests, and they were not able to run enough cycles to actually break these carbon nanotube wires. They finally had to give up and go on to the next test.
Okay, so the carbon nanotubes are stronger and they're lighter. How do they perform in terms of conductivity?
Well, conductivity is the issue. It turns out that carbon nanotubes, while theoretically have a very, very high conductivity, to use them practically, you have to make these bundles, because an actual carbon nanotube is less than microscopic. And so to use them, we have to actually bundle them together. And when you bundle them together, you lose a lot of that conductivity.
And that's principally where your work is then. You're going to solve this conductivity problem.
That's our goal. Okay. Right. What we're doing is we are chemically altering the carbon nanotubes. We're doing a process called intercalation, which means to insert. And we are inserting halogen atoms. These are bromine, chlorine, iodine, in between the bundles. And when we do that, it makes the bundles actually much more conductive. And so what we're trying to do is get to the place where our conductivity is high enough that we can run these as electrical conductors. They're not going to be as conductive as copper, but because the wiring in aircraft and spacecraft is not limited by the conductivity, but by the strength, we're going to be able to save a tremendous amount of weight. We're in the early stages of our research, but we've already developed carbon nanotube wires that have a specific conductivity. That's a conductivity per gram equal to copper.
Well, solution, problem solved. That's great. No, that's a good step, right?
It's a good step, but it's not the only step. Okay. Because right now we're working with very, very tiny amounts. I mean, milligrams of material, and we're going to have to work with kilograms of materials. And so we have both the process of our partners who actually make these fibers have to scale up so that they can make large quantities, and we have to scale up our chemical processes so that we can modify them.
Okay, so scaling up is actually the big challenge.
It is.
Okay, see, for a second I thought if I understood this properly, I'd understand how Peter Parker could shoot web, okay? But apparently with the scale-up issue, not even he could handle it at that.
I'm afraid not.
All right, well, appreciate it. I wish you the best of luck, and I hope soon to see copper wire. Well, I don't want to see them go away, but at least in terms of these aircraft and spacecraft, saving that weight and giving us all the conductivity we need.
I hope so.
It's interesting to see how NASA, as they improve on a technology, just how complex the process becomes. And I never would have thought about it, but creating nanowire is actually a groundbreaking or game-changing technology.
Yeah, and that's a cool area of research that Jim's working on. But another area that NASA's looking at is carbon nanotubes and overwrap pressure vessels. So what they want to do is they want to take a COPV, or a composite overwrap pressure vessel, and spin it with carbon nanotubes.
And those carbon nanotube composites are, as you said, very difficult to work with. So NASA is actually looking at a couple different approaches.
And I had an opportunity to look real closely at least one of those approaches. Let's check it out. We're here with Aslan Biagi, who's the project manager for nanotechnology. So Aslan, tell us about what you're doing with nanotechnology.
Our goal is to actually use the nanotechnology and make lighter materials so that we can reduce weight on the vehicles and launch vehicles.
And I understand you have a big flight test that you're moving toward.
Yes, so our carbon nanotube reinforcement composites that we're developing in the nanotechnology project will later be placed on a composite overwrap pressure vessel, which will be launched on a sounding rocket.
Haven't we launched like composite overwrap vessels before? What's unique about this one?
So COPVs have been on NASA for a long time. The only difference here is that we're using carbon nanotubes instead of carbon fibers, which is the typical material that we use for the COPVs. Now we're transitioning into carbon nanotubes, and that's actually making the material 2 times stronger than carbon fiber and also lighter. And that's the game-changing part of it.
Tiffany, how do you guys prepare for a carbon overwrap pressure vessel test?
So we start off by taking the tensile strength of ring specimens, where we have an aluminum ring and they're overwrapped with a carbon nanotube yarn and resin in a composite structure. And the reason why we do this is to help us predict the load at where our composite overwrap material is failing. So the rings are speckle painted for digital imaging correlation, so we can better determine how and where the failure occurs.
So you guys actually plan in these tests to actually break the rings?
Yes, we test the bare aluminum rings first so we can get a baseline value of the load where the aluminum ring is failing, and then from there we can subtract the failure from the composite overwrap material from the baseline so that we can know the tensile strength of the overwrap material itself.
Have you done actually any tests? Do you know how successful or how strong this overwrap is going to be?
Yes, right now the first layer of material that we're putting onto the rings fell at about close to 600 pounds of force from that small overwrap material. The overwrap material that we're testing is only about 0.36 inches wide.
Nice. Mm-hmm. So you do test on rings as well as full tanks, is that correct?
Yes, the tanks are the end goal, but for everything that we're doing right now is for the ring test to prepare for the ultimate burst test, and that's actually when the tanks will be wound with this particular type of material.
You use that word burst specifically because you really want to pressurize the tank to the point of failure, which creates a burst.
Yes, correct.
Yeah. I hope you're successful bursting the tank.
Thank you. We hope that there's not going to be a really large knockdown in properties compared to carbon fiber composites. This technology at this level is still in the premature stages. We're just trying to help do as much research as possible on these preliminary tests so that we can further advance this technology and get it to the area where carbon fiber composites are currently.
So John, Tiffany gets a lot of data from these tests. How are you using that data to prepare for the upcoming flight test?
Well, what we've done is made sure that we've interacted with Wallup's sounding rocket experts to make sure that we capture the entire flight environment and all the design requirements for our COPV and bring those into the laboratory and have Tiffany duplicate the critical environments that the material has to operate in. This gives me data that I then use to size or dimension the COPV, determine how much nanocomposite is actually applied to meet the performance and safety requirements that Wallops has for their sounding rocket flight. We consider the vibration environments and the temperatures that a COPV will see and make sure that all the forces and loads that are applied to the COPV are accounted for in our design.
How will an improved technology, this game-changing technology, help future missions?
Well, we know that the carbon nanotube is one of the most strong and stiff materials known to man. If we can get that material into an engineering application, we could probably make much lighter spaceflight hardware than what we're doing right now. By adding this small nanotube wrap, we could easily increase the strength of the tank by a factor of 2, with only increasing the weight of the tank by perhaps 10%. So that's an enormous gain in strength.
We're back to continue our discussion on the processes to wrap the pressure vessels. We just saw one. Mia, tell us about another.
Okay, so what we've done here is taken a spool of carbon nanotube yarn And instead of processing it in a large machine, we took the critical steps that we use on the large machine and downscale the equipment. And so what that allowed us to do is take a small amount of material, get the resin infiltrated in it, and wind either a cylinder or a bottle directly from the yarn.
So essentially what you're doing is you're sort of miniaturizing that process.
Correct. So in order for us to optimize the process using the least amount of material and also getting the process done quickly, normally when we do this type of operation, we use a machine that takes up an entire room. Okay, so we've now downsized that process into a tabletop piece of equipment.
Well, what are the benefits of miniaturizing the entire process?
So several benefits come out of that. One is we basically are tailoring the process that we're developing to the amount of material that's available. We can very quickly rapid prototype in a sense. We can try several different conditions very quickly, changing that using the least amount of material. And also it allows us to modify the machine very quickly to adapt to what we learn as we are winding this material.
When you miniaturize it, are you skipping steps? Because when you look at your device, you don't have many moving parts compared to the commercial
That's correct.
size. And so what have you done to get the same benefits?
Okay, so here are the critical steps, right? You take the yarn, which is dry, and then we need to send it through a bath so that the resin will be absorbed onto the yarn. And then after the resin is absorbed, really what we want to use that infused yarn with is to wind it around the bottle. Okay, so in a very short distance, we're able to achieve that. It's in about a couple of feet, right? We're able to see that process right away.
Now that you have the process that has been miniaturized, what is the next step?
So in order to get our article certified for flight, it needs to be made on a commercial scale. And so those steps that we have defined and optimized are now going to be transferred to a space flight center, which is used to building these types of flight articles. And those basic steps are basically now being adapted back to a commercial machine.
And then from there, that pressure vessel will be transferred to the flight facility where it will be launched on the Sounding Rocket in 2016.
Correct. We're going to be launching from Wallops, yes.
Now, nanotechnology began several years ago. Well, it's been around for a while, but from where you started with it, how has it evolved over the years?
When we started working with carbon nanotubes, they were still available in powder form. And because on the nanoscale they had such tremendous properties, people thought we could just essentially sprinkle some on a polymer matrix and get the benefit of these materials. We studied it for several years and realized that is not a method that we can get the type of properties that we're looking for, because we're competing with state-of-the-art structural materials, which are carbon fiber composites. So around 5 years ago, we actually switched approach and worked with a vendor so that we use predominantly continuous format of carbon nanotubes. Now, the challenge there is that in the bulk form, it does not have the kind of properties that were existing in the nanoscale. We had to basically optimize the process to take advantage of these processes and work in collaboration with the manufacturer to also optimize those properties from the starting material. So they had to modify their production process to accommodate this. And so there was interactive exchange of information so that we can both get better material properties. In a span of about 3 years, we've made significant advances that take us far from where we started, to the degree that I can say that just 2 years ago, we did not have the kind of properties we have now.
Right. And where do you see the future, or how close are you into perfecting carbon nano composites?
So
that's kind of a big question.
Perfection, yes, perfection is hard to achieve. So here's the thing. When you talk about perfection, we are comparing against a material that's been around for about 50 years, right? Although we've come a long way when we actually analyze the materials that we have now for carbon nanotubes, they're nowhere near optimal. The good news is, despite them not being optimal, they're already performing at par with some carbon fiber composites, right? There's a lot of upside to this material that we don't fully understand at this point. And so there's very large areas of research yet that we can explore to really tap the potential of this material.
Now, earlier, Steve Gaddis said that they are working for a high reward from high risk. What is the reward you're looking for from carbon nanotube composites?
When we first started looking at carbon nanotubes, the reason we're looking at it is because there's high potential for this material to be a disruptive technology. And the reason is it is multiple times stronger and stiffer than carbon fiber. What we're trying to do now is we are looking to optimize it so that it is at least 2 or 3 times stronger yet than what is possible now. And the reason is there are some applications like access to space, especially if we're going to Mars, where significant reduction of mass is very important because what you launch is hundreds of times heavier than what your actual payload is. So we're trying to reduce the mass of the payload. If we can get 2 to 3 times stronger with a state-of-the-art material, it makes a mission to Mars possible. And that's why we say this is a disruptive technology.
And that is game-changing.
Yes.
You're watching NASA Edge.
An inside and outside look at all things NASA.
Rock, report range status.
Range green.
T-minus 5, 4, 3, 2, 1. Go for main engine start. 0 and lift off.
This is no ordinary aircraft, and on board is no ordinary spacecraft. This C-5 Super Galaxy is hauling something special.
It can carry what no other airplane can carry in the Air Force. Width, length, weight, you name it, it can get on that thing. This jet can do it like no other jet.
After 2 years of construction at Lockheed Martin in Denver and a few hours in the air, NOAA's GOES-S has finally made it to Kennedy Space Center, where the countdown to T0 begins.
It's always exciting to bring a satellite down to Kennedy Space Center and participate in that whole activity of getting a satellite ready for launch.
Getting it out here and rolling it into the launch processing facility, that is a very big deal for us. It's one of the hugest milestones in any spacecraft program is shipped. It's not easy to transport something like this across the country.
And this is where the rubber meets the road. This is where all these people that have worked on this program for a couple of years, it culminates into the excitement of getting ready for what we call launch fever.
And so now, we get to kind of do some of the fun stuff, like put it on a giant airplane and take it to Kennedy Space Center, where we get to prepare it to go onto an Atlas V launch vehicle and launch.
It's the job of NASA's Launch Services Program to get GOES-S into orbit. And they have just a few months to do the final launch preps and inspections before T0 arrives. This is no easy task with a spacecraft of this size and complexity. In spaceflight, there are no second chances. A successful launch is resting on their shoulders. It has to be perfect the first time.
It's very exciting. I love being a part of this, and I love being able to contribute to the spacecraft and to its success.
GOES-S is the second part of a weather satellite upgrade project NOAA is undertaking, destined to save lives by modernizing our weather forecasting ability.
We have a very young team, and this will be their first campaign. So we're trying to put the excitement into that, let them feel what it's like to touch the spacecraft for the last time. Launch operations is time we all get together for one goal, which is launch.
But achieving that goal will not be easy. The road to T0 has just begun. There's only one cargo ship designed to transport rockets for United Launch Alliance. And tonight, it's pulling into Port Canaveral with the robust flight hardware of an Atlas V.
We're a high-tech vessel, high maneuverability.
We have to be because we get into some tight areas on shallow rivers. The Delta Mariner is unique. It has 2 aft Z drives coupled by computer with the bow thrusters that turns 360 degrees on demand.
This crew has work to do. In less than 4 weeks, the rocket must be safely delivered, inspected, and assembled in order to successfully launch NOAA's highly advanced GOES-S weather satellite.
I sense from the crew the pride being part of this mission. And when I put this vessel alongside the dock, it is a very accomplished feeling that we all have.
The arrival of the Mariner is the start of operations for the flow of a rocket.
Teams from ULA and NASA's Launch Services Program start by unchaining the Atlas V booster and Centaur components, wasting no time in developing a plan and getting organized for transport.
We're going to take the booster over to the ASOC. It's going to be Convoy 1 to be the leader, followed by the booster.
It's a very exciting day for the vehicle system engineers as we're offloading the launch vehicle that will carry the GOES-S satellite.
Here comes the Centaur second stage, with its pressurized stainless steel tank as thin as a dime. Unable to support its own weight until fully fueled, it's carried off the ship by a specialized trailer. Next comes the Atlas V booster, all 106 feet of it. This booster and 4 solid rocket motors have one job: provide enough energy at liftoff for the entire launch vehicle and payload to overcome the pull of Earth's gravity.
I never get tired of seeing the rockets come in. It's very exciting, especially on the Mariner.
Now on land, a challenging cross-base transport lies ahead to the Atlas Space Flight Operations Center. Inside this multifunctional facility, crews will remove the protective coverings, inspect the hardware, and install the final flight components. For now, this mission remains a go, but the highly complex job of stacking the rocket is still to come. ODark 30, Cape Canaveral Air Force Station. With a full week of intense rocket assembly activities ahead, the teams from Launch Services Program and United Launch Alliance are getting an early start. It all begins with the booster. The booster is the backbone of the Atlas V, and literally everything is riding on it. It's the largest component and first to be lifted.
So Launch Services Program partnered with United Launch Alliance to select the Atlas 541 vehicle because it is one awesome rocket, and we need that for us to get GOES-S to its geostationary orbit to meet its mission requirement.
It will take more than just the booster to get all the way to geostationary orbit. That's why we're adding 4 solid rocket boosters.
When you start with the Atlas booster, it's like 860,000 pounds of thrust with just the RD-180. So we need the solids for extra performance. We need it to get heavy payloads off the pad and for additional performance going to geosynchronous orbit or geotransfer. Mating the solids to the booster is a very hazardous operation. We have safety with us at all times. You have 100,000 pounds going up into the air and hanging on a crane. And oh, by the way, it's explosive.
Once the solids are mounted, it's time to mate the Centaur.
The Centaur is the upper stage, and it's tuned. It's like a highly tuned race car. It's light, it's efficient, it performs well for us.
We're out here to do the job and get it done right. If you see something that's not right, bring it up to us. Let's give us a chance to fix it, okay? All right, let's get in position to do this thing.
Assembling a rocket can make or break any mission. It takes tremendous coordination and skill to get this job done. The team makes it look easy, but rocket science never is.
The coolest part of my job is coming down here and seeing the hardware and knowing what it's capable of. We all get to work with rockets, and it's really exciting and fun, and everybody has their part in all of that. And yeah, when you're out with friends, you can say you're a rocket scientist. I do.
So there's really nothing quite like all the work and all the setup that we do to get ready to do this and get built up a rocket and tested to get to launch day. And when we get to T0 and the rocket lifts off and the control room rattles and shakes a little bit, it's an awesome feeling. That is the ultimate reward, and that's really what makes us happy, what makes our customer happy, is putting our customer where they want to go in the right spot in the exact right orbit, and that is, there's a lot of pride in that.
This rocket is almost ready to roll. Of course, the only thing missing is its GOES-S payload. 2 weeks to T0. Today is another huge milestone for NOAA's GOES-S mission.
So today we start something called encapsulation. By encapsulation, we actually put a container around the satellite. It's called a payload fairing. That payload fairing will protect the satellite for the first 3.5 minutes of its mission. It sounds like a very short period of time, but in fact, that's when we would have the maximum aerodynamic and acoustic loads on the satellite. So we're trying to protect the satellite. Right now, we really have tested everything we need to do to make sure this satellite is ready for launch. The next time we'll see this satellite is on orbit.
Shooting off the launch pad like a bullet, this vehicle will rocket past the speed of sound in just over 30 seconds. If not protected, the Earth's atmosphere will rip GOES-S to pieces. But for a satellite designed only to live in the vacuum of space, life on Earth can be just as dangerous. Any exposure to dust or moisture could contaminate the satellite and destroy the mission. That's why this fairing is more than just a suit of armor. It's also a portable clean room. With encapsulation complete, it's time to call in the KMAG. This 72-wheel transport vehicle is what it takes to get this massive payload to the pad.
Spacecraft hoist and mate to the launch vehicle today is a huge milestone for the whole operation. And this is the biggest integrated operation that we've had so far. And it goes all day, goes all night, from transport and then hoist and mate, and it'll go into the evening tonight as they finish closeouts.
After working through the night, LSP and ULA are almost there. Just 150 feet to go, straight up.
Obstacles, we do have obstacles on the decks, on the KMAG, so watch your step, walking area, trip hazards, and then remember about your hard hats, chin straps. Any other questions? All right, let's go do this.
There's a lot of moving parts involved with processing a spacecraft, processing a rocket, and then bringing them together for a launch. There are a lot of people involved, and there are a lot of moving parts. We have a lot of hard timelines that we have to meet and deadlines that we have to meet, and everybody works as hard as they can to meet those deadlines, and sometimes we have to work around the clock to meet those.
We've reached a critical point on the road to T0. GOES-S is now mated to the Atlas V.
We've been working for several years integrating this thing and completed that now. We've got the satellite on top, and we're ready to go.
With all major milestones complete, this rocket is ready to roll.
Engineer, proceed with MLP transport to pad.
Roger.
It's go time. The GOES-S launch window opens tomorrow. ULA and LSP have one last critical procedure to complete. Get the entire Atlas V stack and its mobile launch platform to the pad.
It is a fairly challenging activity if you think about moving a 1.5 million pound mobile launch platform and vehicle out to the pad.
Once it gets there, it will be loaded with rocket fuel and be ready to start the terminal count to T0. Years of intense planning and coordination are finally rolling to the pad, and the majesty of the Atlas V is on display as it inches its way to liftoff.
The thrill of seeing that Atlas vehicle, all 197 feet of it, rolling up to the pad, it's just really exciting because I know that means tomorrow is launch.
GOES-S is particularly important because of how it's transforming our capability to predict weather and protect lives and property. And I can't wait for it to launch tomorrow and become operational.
So great to be here after a number of years of seeing the spacecraft come together and all the instruments integrated onto the spacecraft. Our baby is tucked in and ready for launch tomorrow.
This is the LC-1 performing pre-test briefing. This operation is classified hazardous. Cryogenics will be loaded. ALC verified count to start at 1947 Zulu. Verified. Proceeding with the count.
We're launching today, and the ULA team got on console a few hours ago, turned power on the rocket, and we are counting down to T0 right now. I'm on my way over to the ASOC, the Atlas Space Flight Operations Center,
where the Mission Director Center and the Launch Control Center are located. And if the range is clear and the rocket is good, we're go for today. I love launch day. I'm so fortunate to work with a great team. Our team gets so incredibly excited to do missions, and it all culminates today.
Range coordinator. Clear to proceed. Launch director, you have permission to launch. Proceeding with the count. ALC verified T0 is set for 2202 Zulu. Verified. Rock report range status. Range green. Status check. Go Atlas. Go Centaur.
Range Operations Controller reports range green. Everything is go.
7, 6, 5, 4, 3, 2, 1. And liftoff of Atlas V. And
I think every person who comes to work for NASA dreams of being part of that spacecraft development program, that you get to see it launch and you get to see it send humans to the next step in the frontier. Of space, right? And I think every one of us started with that.
Okay, to start, first tell us a little bit about how you got here. And then if you could share with us who Monica is.
Okay. Well, I've been out here 12 years. I'm a research laboratory mechanic. They hired me on actually as general labor. And said if I did really well, I had a chance to get into the NASA apprentice program. So I did really well, and I got into the program. They sent me to school, and then on-the-job training. Hours to learn the skills that I needed for here. And I guess the rest is history.
I'm Cale Yeager. I'm part of the Research Laboratory Mechanic Apprenticeship Program.
Okay, my name is Steve West. I'm a test facility coordinator here at SEC. Been here a long time. I think I'm on starting my 37th year. If you want to do the math, I think it's pretty close to that.
My name's Erin Reed. I'm a test engineer here at SEC.
I'm Nicole Smith. I'm the project manager for Orion testing here at NASA's Plum Brook Station. For the better part of the last 12 years, I've been working on some form of Orion with a slight detour to be a legislative fellow on the Hill for the senior senator from Ohio.
At the end of the 4 years that this apprenticeship is supposed to take, I'll come out as a research laboratory mechanic, have my journeyman's card, and go from there. I've always been a big space nerd, always been a fan of outer space and space travel, and the big question of how do we get here. Just always been very intrigued by space. I'm inclined mechanically, I go with my hands, I like building stuff, troubleshooting. So it kind of worked out that I got to partner my skills with my desires and my what I enjoy.
I would say my main role out here is an operator, especially during test time. I run the compressors for the cryo shroud that changes the temperatures in the vacuum chamber. So, and offloads of liquid nitrogen and gaseous nitrogen.
I'm the contamination engineer here. So when I first got here, the facility has generally only been used for large-scale fairing deployments. And so they're not really clean. They're not meant to be in a clean environment. So the vacuum chamber that we've used has always been sort of dirty. And so when I came here, there was a big push to try to figure out how to clean the chamber and how to make the facility clean enough so that when we got a flight vehicle, we wouldn't contaminate the vehicle.
We are standing very high up in the Assembly High Bay at the Space Environments Complex at NASA's Plumbrook Station.
We have a vacuum chamber, environmental chamber that we provide the environment for space. We have the world's largest shaker table. We have the most powerful reverberation chamber, which is capable of producing 163 dB. The shaker table, that is for the sound. When you take a rocket and you pound it with the sound that makes when it, at liftoff. So there's a lot of capabilities that this test facility now has. At one time it was just the world's largest vacuum chamber with the world's largest cold wall. So it's much more now.
A lot of the technicians and engineers here are very hands-on, and we have very diverse backgrounds. And it's really important to be able to take that diversity of experience and bring it here to solve problems. Like, you'll have Monica out helping offload all of the nitrogen trucks. We'll go through about 12 to 14 nitrogen trucks a day when we're running the thermal vacuum chamber. You'll have Kale over driving the door. I think he's down there cleaning the floor right now. Everybody is hands-on and does a ton of different stuff. Erin Reed is an example of one of our test conductors, right? So she's going to be that point of contact in between the facility team that's running the vacuum chamber and the vehicle team. And then you've got the people who've been here for a really long time who manage a lot of stuff and make sure that all the gears keep going. So like Steve West will be managing all the technicians, where they're deployed, helping with all the operations. Sometimes you'll see him down here on the crane lifts. And then you have someone like me who's the project manager who makes sure that all these people have all the resources they need. I'll make sure that everybody working on the team knows all the information that they need to know. So we're just trying to tie it all together and keep everyone moving in the same direction.
We are all very diverse as far as our personalities, and we're all very accepting, and we all love to just have fun. I think that's probably the biggest part of what makes this team work, is that no matter what type of day you're having, no matter what type of work we have to do, we're always joking around, we're always having a good time with one another.
It's a tight-knit group that, I work with, and everybody's pretty accepting here. I do think it's cool for women to see they can break out of maybe a traditional job. That's a good thing.
I really like the people I work with, everybody I work with. We all work really hard, and it's really nice to know that when you're feeling overloaded with work, that the people next to you are just as overloaded. Misery loves company. But more than that, we're all working together towards a common goal. So there are lots of disagreements that we have, technical disagreements. We may see things with a different perspective, but we all know that it's because we're trying to create the best solution for what we're trying to do.
I mean, data's our product. We don't make any widgets or anything, so that's our product. So I believe the engineering and the techs here are outstanding. I would put them up against anyone in the world.
So the thing that's different about having Artemis here is that it's a real piece of spaceflight hardware that's going to be launched when it's done here. So we do a lot of other test articles to prepare. All of the other prior Orion hardware was development. So this one it's huge, and it's going to go around the moon. And we're going to be able to sit there and watch it launch and watch it while it's out on its orbit and see how it's doing and say, yeah, we had a huge hand in that.
I've been here so long that I've seen the transition, and it's so neat to finally see. I spent a lifetime getting it to where it is, and I'm really proud that we're testing flight hardware now. I think it's a credit to the people I work with. I work with some great engineers and great technicians, so very proud of what we've accomplished.
When it's a flight vehicle, you're not just concerned about the data from the test, you're actually concerned about the vehicle itself, because that's the thing that's going to be delivered to space. So that's when it becomes a higher risk.
During the thermal vacuum test, we'll provide a really cold background of space with our cryo wall, and then we'll be able to do different zones of heating to simulate being in a specific part of the orbit where one part of the spacecraft might be in the sun and the other part is in the shade. When we're done with the thermal vacuum test, we'll bring it back out, do some reconfiguration, and then put it back in that chamber, but instead of pumping the air out of it and putting the cold wall in, we'll actually hit it with radio frequency waves to do electromagnetic testing.
When you get in the test conditions and you got the chamber pumped down and the cryo shroud's at the temperature it's supposed to be, it can get very boring because everything's running perfectly, but boring is good. And to me, it's exciting. You're part of the crew, you're part of history, really. So I think that's very neat.
We face challenges almost daily, which is part of why I love this job. I mean, we don't do the same thing every day. We do something different. We respond to changes. Everything we do is schedule driven for the most part. So when schedules delay or schedules, we have to redirect. And that's a challenge in itself. But we keep our crew working very effectively all the time, which is a challenge. And I get excited about those things.
I think the biggest risks are for your optical components. For instance, we have a star tracker on the vehicle. So if you can imagine if a particle of dust or some bit of oil got stuck on the star tracker and the computer sees it as a star, but it doesn't move no matter how the vehicle moves, that would change how it's going to try to navigate, and it might even mess up some of the algorithms. So there's a lot of those sensitive surfaces that we're concerned about.
If something gets contaminated with the spaceflight hardware, it can be detrimental when they go to launch it. From the oils from your hand, anything can gas off going into space. You're contaminating the test starter that's coming if you touch it with your fingertips even. So we have to be that careful because it is spaceflight hardware.
Outside of work, I have a 4-year-old son and 2 8-month-old sons. We had twins over the furlough, so that was exciting. I'm lucky. My girlfriend is very supportive. She helps out a lot. She makes it easy. Having the twins at home is very tough because she gets run ragged. I get home just in time for bedtime. Luckily, as far as school goes, I'm doing online courses this time around, and hopefully we'll be able to complete just through online courses. But yeah, it's definitely tough to balance it. It's very tough.
So it takes someone that's motivated to try to get it all done. And sometimes I have to sacrifice a little bit one way or the other, because I do have a family. But I love this job. My kids are happy I work here. It's just a good thing. And it's very, very exciting.
It's huge for me to be a part of it and to see the spacecraft come here to Ohio and be tested for 4 months and then see it launch. And I'm really excited about people going back to the moon. So the idea of the first woman stepping foot on the moon and me getting an opportunity to work on this spacecraft here, it's huge. So I'm really excited for that.
Wow. Yeah, it's really coming to our facility. This is history. This is pretty cool.
I think it means everything. I think this is the next small step in humanity's exploration of the universe. Because this is going to help us not just get to the moon and not just get to Mars, but then it's going to be the jump-off point to the next place we go. I really feel it's a really awesome thing to be part of. We are taking that next step. We are doing that next great leap.
You think about all of the thousands of people who worked on this vehicle and worked on all of its testing. I'm such a small part of this program. I'm not even a blip on how this program functions, but it takes all of those people to make something like the Orion vehicle at Artemis successful. And so I'm happy to be a part. If that's the part I need to play, I'm happy to be a part of it. So it's exciting.
Well, I'm a real go-getter. I like to go, which helps me for this job because we do put a lot of hours in. I used to be in the apprentice program, so I was going to school. At the time, I had 3 younger kids. That's me. Yeah.
Mars.
Wow.
Yeah,
I didn't know
Mars.
you could do that, Tim. Hi, I'm Jenny,
And I'm Tim.
and we are here to get some of my questions about Mars answered.
Mars. It's an awesome planet that's right next door.
Right next door? Really?
Well, not right next door, but it's close.
It's pretty close.
Mars, it's one of our closest neighbors in the solar system, and there's a lot of signs that there used to be a lot of water at the surface. And so, if you can understand what Mars is like now and what it used to be like, tells us how planets form and change over time.
How is it similar to Earth?
It's got weather, it's the day length is about the same, and there's different climates, there's seasons, it's tilted about the same as Earth right now.
How is it different than Earth?
Well, it's a lot smaller, first of all. Another big difference is the atmosphere is really, really thin. It's only about 1% as thick as the Earth's atmosphere. It is bone dry at the surface right now, and it's a lot colder. We actually detected snow on Mars using a Canadian instrument on the Mars Phoenix mission.
Wow, trust the Canadians to find the snow, huh?
Who else would do it?
Okay, tell me more about some interesting features that are on Mars. What do we see now that we really want to study?
There's lots.
There's
it's,
lots?
It's an amazing planet. There's the largest volcano in the solar system called Olympus Mons. Wow. It's over 3 times the height of Mount Everest. Not active anymore, but it's a giant, giant volcano. There's a huge valley that's about over 5 kilometers deep called Valles Marineris. There's features that tell you where there might be ice under the ground. There's all kinds of incredible things. Old lakes, old deltas, lots of craters. It's one of the only places in the solar system